Okay. In this section, we are going to discussing about different kind of fast-acting actuators and what are the dynamic and static characteristics of different kinds of fast-acting actuators. And some kind of actuators we have already discussed in this class, in this module, disc, plugger, conical, and ball armature-based fast-acting actuators. And these are the basic solenoid configuration that we can applicable for different application, different provable application in different fields. And each of the configuration has unique features that predetermine application also. And obviously, with the aid of this kind of design, we have some pros and always some kind of cons already analyzed in the system in sense of fast acting actuators, disc plugger, conical, and ball armatures. And solenoid, we can divide it in three category inside of the architecture in base. A stationary magnetic circuit it have, and all it have a coil with a current source, and it have a magnetic armature. And these three things should always a fast acting actuator should have. And additionally, the main air gap region can be specified separately to maintain the linear displacement of the armature and prevent shrinking the air gap to zero, which may cause converging problems normally in sense of fast acting solenoids when we are or actuators when we are going in deep. Okay, and this are the four types of solenoid we will discuss in this module in detail. Disc solenoids, plugger solenoids, ball solenoids, and conical solenoids. And moving to the next slide, disc solenoid. And this is the structure of disc solenoid. And the disc solenoid it consists of a disc armature, and we have a coil, a stationary magnetic circuit, and the armature and coil stationary magnetic circuit is separating with an air gap. And this air gap is required for the movement of the disc armature in a proper way. We can say that. Okay. And as an initial investigation, we have already discussed about the plugger solenoid internal things and also how how the plugger solenoid is working and how the movable part is moving when it is get excited. Okay, and so the air gap in the system is very important, and the design and the architecture of the disc armature is little bit important in the field of different application based on vehicle application already. The disk solenoid configuration has doubled the main air gap for the flux cause as shown in figure. And when the system is excited, and due to the excitation, the electromagnetic system will get excited with the help of electromagnetic fluxes by the generation of electromagnetic fluxes, and that flux will influence the disk armature to move towards our core side or coil side or stationary magnetic circuit side. And with the aid of this air gap present in the system, this disk armature will move when this coil get excited. Okay, and that is normally is happening in all kinds of solenoid system that we are discussing in this module. At the same time, it has two relatively large surface inner pole outer magnetic circuit around the coil where the flux perpendicular to its surface at least uh, at the small air gap is enough. Okay, even though its small air gap is lying over here, it is capable of moving the disk armature through this small air gap when the system is excited. Okay, and that magnetic flux is perpendicular to the disk armature always, and this promotes the application with small travel fast action. A small travel would be secure high solenoid electromagnetic efficiency, where large force would be helped to complete the travel distance in a relatively short period of time. And due to the small air gap, our system is capable of handling the rapid responses, handling the rapid responses and rapid activations. And so normally this solenoid is used for injectors, where are the attributors, injectors in the fuel pumps, and also injectors in the normal printing devices. Okay, the dynamic characteristics of this solenoid and the static characteristics of this solenoid we will discuss in the next slide. Okay, and this is the static characteristics of the disk solenoid. Static is nothing but we are normally analyzing the system based on time by applying an external force or external voltage to the system. What are all the things happening in technically, and how the applied voltage is gaining by the system, how flex is linking inside the system, how net forces is affected in our system, how the spring force is affecting in our displacement, and how displacement is happening inside the system, and how maybe the current is changing in the system. This all thing we will discuss in detail in designing aspect for the better efficiency of the solenoid actuators. And that's why this is characteristics is known as static characteristics. And normally engineers will discuss two kinds of characteristics over the design aspect. When we are looking for the design aspect, static and dynamic characteristics. And now we are going to going to see in detail about the static characteristics of the solenoid. That means this solenoid. And the disk solenoid, when we are applying the voltage, and normally if we are applying the pulse, we have already discussed, like in the case of PWM, we are applying a high pulse, and then we are applying a low pulse, high and low. And what are the changes happening in sense of flex? And the flex is increasing up to a tip, then decreasing it, and it's moving to the stationary position. Okay, when you are applying a voltage like this, and the flux inside the system is increasing like this, and suddenly rapidly it's increasing and rapidly it's decreasing, like shown in figure. Okay, that is happening inside in the case of this solenoid, and this may different in the case of plugger solenoid. This may different in the case of ball solenoid. That the static characteristics always differ in the case of different architecture. Okay, I mean to say here that, and current is also it going to the peak, and it comes down when the applied voltage is going to the low peak. And the net forces inside our system is also initially is not going to at the a peak position. After completing the voltage first phase, it going to the high, and when it is reaching the low, it's automatically reaching gradually reaching the low position, and again it's coming simultaneously or continuously keeping the name structure of the graph when we are applying the voltage like this. Okay, and spring force also, and we already mentioned that we should have a spring action inside in the system for moving our normal movable part into a normal position. It moving back into a normal position, we require a spring force, a simple engineering we require. And the spring force is changing already when the flux is linking to the system, and based on the applied voltage, that's also represented here. And displacement, we can say that initially we have a displacement, maybe it's in the normal position, it may be moving to the forward position or backward position. Anyway, it going for some kind of displacement. That displacement occur according to the voltage that we are applying to the system. And that voltage, when we are applying to the system, your solenoid will not give you the rapid response up to a time, and maybe it's in the case of microseconds. And after that only your system is moving to the position or normal position to the movable position, and coming back to the original position. And when we are removing the applied voltage, when it is going at the neutral position. Okay, and this is a static characteristics. All of you should draw this diagram in your notebook, as well as we will have a correct outlook on this in the point of university examinations. And moving to the dynamic characteristics. Okay, and anyway, we have already applied a force or a voltage over the device, and we analyzed some kind of change that is happening in sense of current, force, flux inside the system. And in this, we will discuss only the dynamic characteristics and how the magnetic changes or magnetic flux linking inside the system in the case of disk armature. Now we can see in deep. Okay, I will show you. And here we can say here a gap is there, disk armature, and some air gap is there. And when we are starting to applying the high voltage, and we can say some lines over here, and that is nothing but the magnetic flux. And magnetic flux is increasing, gradually increasing, and the air gap from disk armature to the coil is decreasing. And that is the a diagram day is showing the at the position of the disk armature at 1 millisecond, and position of the armature at 2 millisecond, and position of the armature at 4 millisecond at the diagram of C. And as time goes up, the disk armature comes near to our coil, then the air gap is reducing, and also the magnetic flux linking of the system is also increasing. Just I mean to say that. Okay, the air gap is decreasing, you can visible that, and the magnetic flux is increasing. Okay, as go the time up. Okay, when we are applying the voltage to the system. And this is how the magnetic flux is orienting throughout the system when we are applying a force or when we are applying a voltage in a different time period. Okay, so we can conclude here. If you are, even though if you are applying the voltage, and the system will give you the rapid response, but in specifically if we are analyzing the rapid response, it is not a rapid response, it is a gradual response. Okay, okay, initial condition it should be like this, and in second at 2 millisecond, if you are directly in these four cases directly we are applying the voltage. Okay, we are not applying the voltage, we are applying the voltage to the system in these four cases. Okay, in the first case, at the if you are applying the voltage, and we are considering this diagram after 1 millisecond, we are considering this diagram after 2 millisecond, and this for 4 millisecond, and flux after 6 millisecond. Okay, flux is increasing and the air gap is decreasing. Okay, and that's all about our this armature based solenoid, disk solenoid. Okay, and we will discuss next solenoid